Hi everyone! In this video we will look at line spectra. The discovery of line spectra was an important piece to the development of atomic theory and our current understanding of atomic structure. We are familiar with the idea that if we apply energy to a solid material in the form of, say, heat or even an electric current, that material will eventually reach a temperature where it emits electromagnetic radiation in the form of visible light. And what we end up seeing is a glow. And this glow is, of course, black body radiation. And that's exactly what's happening in our incandescent light bulbs. These contain a tungsten filament, and when an electric current is passed through it, it eventually reaches a temperature where it emits light. And this particular light source is a white light source. Now, white light is something that we are all familiar with. It's the type of light that comes from the sun and lights all around our home and workplace. But if we look at this light a little closer, let's say with a diffraction grating, we might be able to see white light in a different light. So a diffraction grating is an inexpensive device that you could purchase, and it contains a little material here that has hundreds of lines per millimeter, and each of these lines will work to separate the light into its component wavelengths. So, for example, if we pass light through this, various wavelengths will diffract at different angles, and that's what allows for the separation. So it so happens that if we pass white light through this, we see what we know as a spectrum. And the spectrum for a white light source contains all the possible frequencies or wavelengths of visible light. And this sample of a spectrum from white light is what we know as a continuous spectrum. Another spectrum that you have probably seen before is that from a laser. A laser is an example of a monochromatic spectrum because a laser will emit only one specific frequency of light. It is not possible to separate this light into other distinct colors. We've seen solid materials emit white light at sufficiently high temperatures, but what about gases? So if we take those closely packed atoms in a solid and we separate them so that we have a gas, we now have individual atoms in the gas phase. And these gaseous atoms can be placed into a sealed tube, and we can place this tube in a power supply and then run an electric current through it. And that electric current is, of course, a form of energy. And that energy works to excite the atoms within the gas tube, and they emit electromagnetic radiation, some of which is in the visible light spectrum. And we can analyze this visible light, again with a diffraction grating, and see what we observe. Let's take a look at the spectrum of hydrogen. We should notice a significant difference between the light emitted by the hydrogen atoms compared to the light emitted by black bodies. This is not white light that is composed of all the possible wavelengths in the visible spectrum. This contains only a few discrete lines, and that's where the name line spectrum or a discrete spectrum comes from. Hydrogen contains 4 lines of light, and combined they give the color that we see. We can look at helium as a second example of a line spectrum. If we apply an electric current to helium atoms in a gas tube, we see a different color of light produced. And if observed through a diffraction grating, we can separate those component frequencies or wavelengths. And we see several more lines here than were present for those emitted from hydrogen. Neon is another example we have here. And you've probably seen this characteristic red glow before in neon signs. So neon signs use neon to produce this characteristic red color. And if we inspect this red light with a diffraction grating, we will see again what we call the line spectra. And I hope you've noticed so far that we've looked at hydrogen, helium, and neon, and we've seen very different line spectra from each of these elements. And in fact, each element will produce a unique line spectrum. It's kind of like a barcode. Each element has a unique barcode, just like each thing you buy at the grocery store has its unique barcode that identifies it as that particular item. The emission spectrum of these elements are something that we can use to identify them in the lab. So how does line spectra tell me anything about the structure of an atom? Well, the observation of line spectra actually implies that the energy levels within an atom are quantized, meaning that there is space between the energy levels and that space cannot be occupied. So rather than having a continuous energy spectrum, we have this staircase of energy levels. And it starts with the ground state. And this would be the lowest possible energy that an electron could occupy, and we'll call it E1. It's my first energy level. Then we have what is known as excited states. And we'll go ahead and draw in two excited states here. This is my second energy level, and this is my third energy level, known as excited state 2. This is excited state 1, and it will be the third energy level. Now, an electron within an atom could exist at this energy, or this energy, but could never exist between these energy levels. It's just like us, if we were climbing a staircase. We could climb up the stairs and exist on any one of the stairs at a given point, but we can never be between stairs. So when an electron absorbs energy, say energy from that electric current or the heat or the form of light, this is known as absorption. And those jump from the ground state to one or the other excited states that are available. Then, once the atom is excited, it can relax and lose that energy that it was given. And that relaxation is known as emission. And these will typically emit a photon in the form of light. And that emission is where we get those discrete frequencies or wavelengths of light that we see. So we have just learned that each line in the line spectrum for the elements is due to an electronic transition. That is, an electron within the atom is jumping from one allowed state to another and emitting a photon in the form of electromagnetic radiation, some of which is in the visible light spectrum, which we can see. So it turns out that a mathematician, believe it or not, was able to look at this data and come up with a mathematical relationship that allowed him to predict the wavelengths of light that would be emitted by the hydrogen atom. And his name was Johannes Rydberg, and he said that 1 over the wavelength was equal to some constant. We call this the Rydberg constant. It is equal to 1.097 times 10 to the 7th reciprocal meters. And the meter is important because we will end up with a wavelength in meters when we calculate this out. This constant is multiplied by 1 over n1 squared minus 1 over n2 squared. And n1 and n2 were integer values where n2 had to be larger than n1. And so this is known as the Rydberg equation, and all it does is simply predict the wavelengths that are possible for the hydrogen atom. It doesn't get into anything at all to explain why. And so that's where we're going to go next, is try to understand why we see the specific colors that we see. And that's where Niels Bohr comes in and his model of the atom. So stay tuned for that. I hope you enjoyed this video on line spectra. Please let me know if you have any questions, and thank you for watching.